In this video, I will be explaining you Jordan's theorem. You can see this theorem in the 4th unit of measure and integration. Okay, here you can see the statement. So, if they ask you this Jordan's theorem in the examination means, first thing should come into your mind is function f. Okay, and this function f is of bounded variation on this interval. This interval is a closed and bounded interval. Okay, so what you have to write is f is of if f is of bounded variation on closed interval a comma b, if and only if f is the difference of two increasing function on closed interval a comma b. What is mean by f is the difference of two increasing functions? You can see that here f is the difference of two increasing functions means this format. Here you are having the function f and this is one increasing function and this is another one increasing function. So you can say f is the difference of two increasing functions, right? This is what they are saying in the form of in the sentence. Okay, so let's see. I hope you feel easy to learn the statement of this theorem. So let us move on to the proof. Here you all know this statement is if and only if statement. No, so we are assuming f is of bounded variation on closed interval a comma b. By assuming that, you will prove f is the difference of two increasing function on closed interval a comma b. So what you are doing is you are assuming f is of bounded variation on closed interval a comma b, and before writing to prove from the statement, in between you are having a lemma. Okay, you are writing the statement of that lemma. Let's see the statement of that lemma. If f is of bounded variation on closed interval a comma b, then f has the difference of two increasing function on closed interval a comma b like this. So this is a lemma, already proved lemma. You are using that statement here. Okay. So next line what you are writing is, from this, using this lemma, you are going to say yes, if f is a bounded variation. You are having f is of bounded variation in the assumption, no? So you can say f as from this lemma, you are going to say yes, f is the difference of two increasing function. That is what you are going to do. So after writing the statement of this lemma, you are writing to prove f is the difference of two increasing function on closed interval a comma b. Just copy down from the question. Now by above lemma, from this lemma you can say, in our assumption you are having f is of bounded variation on closed interval a comma b, no? So using that lemma, now you can say f is the difference of two increasing function. So you proved the first part of this theorem. Now let us move on to prove the converse part of this theorem. So in the converse part, you are assuming f is the difference of two increasing function on closed interval a comma b, and you will prove f is of bounded variation on closed interval a comma b. So let's see the proof. Conversely, assume f is the difference of two increasing function, and what you are going to prove? To prove f is of bounded variation. So f is of bounded variation means what you are going to prove? That is to prove total variation of f less than infinitive. This is what the condition you are going to prove. How you are saying it is enough to prove this? Why you are proving this? By the definition of bounded variation, you are writing like this. Okay, f is of bounded variation on closed interval a comma b means what you have to prove? Total variation. How to read this? Total variation of f less than infinitive. This is what we have to prove. Okay, to prove this, what you are doing is, you are taking like this, f of x equal to g of x minus h of x. You are taking like this. Okay, let f of x equal to g of x minus h of x, where this g and h you are having, no? This g and h are increasing functions. Where it is increasing functions? These two are increasing functions on closed interval a comma b. This is how you are taking. Okay, to prove this part. Now you are going to partitioning this interval. Okay, like this. P is equal to a equal to x naught, then write comma I missed to write this a and b here, okay? So you write it properly. A equal to x naught, comma x1, comma etc., comma xk equal to b. Like that you have to write. Then close this curly braces and then be the partition of closed interval a comma b. Right, like that. So first what you did? First you are taking f of x equal to g of x minus h of x. And then what you are doing? You are taking a partition on closed interval a comma b. Here it is. Now consider, you are considering like this, okay? Variation of f comma p equal to like this. You are having all these things in the definition. Okay. Look at this. Define the variation of f with respect to p by, you are defining variation of f like this. In the definition you are having all these things, okay? You are using that in our proof. Also here you look at this. Bounded variation on closed interval a comma b means what? This condition, okay? These are all you are writing from the definition of what? What? From the definition of bounded variation. Okay, here you are having a remark, okay? They may ask you this remark in the 1 mark questions. Let's read it. If f is an increasing function on closed interval a comma b, then f is of bounded variation and this condition. They may ask this, okay? Somewhere I saw this 1 mark question. In the previous year question papers, I saw this kind of 1 mark question. So be ready with this 1 mark question also. Okay, here. Let's continue our proof. So you are considering this, okay? So after that what you are doing is write the summation I is equal to 1 to k and put the modulus, and f of x means g of x minus h of x, no? So if f of xi means what? G of xi minus h of xi, no? So that is what you are writing. In the place of f of xi, here you are substituting this, and in the place of f of xi minus 1 you are substituting this. How? Using this, okay? If f of xi minus 1 means what? In the place of x, now you are having xi minus 1. So you get g of xi minus 1 minus h of xi minus 1. Is that clear? So that is what you are writing. Before that, you don't look at this. Here, if you look at this, you may get confusions. Before that, after writing this, look at this. So, write summation I is equal to 1 to k. Then put the modulus. Can you see that? I wrote it using the pencil, okay? So, put the modulus and then substitute the values as I told you. The place of f of xi, in the next step you are writing this and then you are writing this for f of xi minus 1. Now what you are doing is you are splitting the modulus. So when you split the modulus, this inequality you will get, right? Less than or equal to, split the modulus like this, so that you will get this, okay? Look at this. Here if you look at this, you will get some confusions because some steps are missing. So that is why when I learned it, I realized that if we follow this, we may get confused. So that is why in this place I wrote it in a perfect manner. Each steps are there. So please look at this. Splitting the modulus so that you will get this. After that what you are doing is, from here you are taking minus common, so that within this modulus a small changes is happening. Now here you are having minus inside the modulus, no? So when you write it without modulus, this minus will be cancelled, no? That will happen, no? Because minus is within modulus. So when you remove the modulus, the minus will also disappear. So that process will happen and finally you will get this line. Okay. After that, you are giving I is equal to 1 to k value to these, so that you will get this. After that, all the values will be cancelled except minus g of x naught minus h of x naught. Okay. Then plus h of xk. These values will remain. So here in the next page you can see the remaining terms. These are the terms only you will have. All other terms will get cancelled. So you are having in the partition, you partitioned closed interval a comma b, no, in a step. So there you have wrote A not equal to what? A equal to x naught and B equal to xk. You wrote like that, no? So you are applying that here. In the place of xk, you are putting B. In the place of x naught, you are putting A. And so that you will get this line. Now writing the left hand side and right hand side. Now taking supremum. Supremum, you will get this. This value will be less than infinitive. That is, it means what? This value will be finite. When you find the value of these, you will get a finite value, right? So that is why less than infinitive. Less than infinitive means what? It is finite. That is what the meaning. So now you got supremum v of f comma p means by the definition you can write tv of f. So that is how comparing these two you are getting tv. Total variation of f will be less than infinitive. So this is how you have proved, no? You got this. So you can say f is of bounded variation. Hence the proof.